This is lecture 9 of CS147 Computer Architecture Study. We'll be concentrating today on digital circuit that can perform integer addition and subtraction. We'll see how we can build up such digital circuit which can perform integer addition and subtraction. In this regard, like just to mention, in this course we won't be dealing with floating point operations. These are out of our scope for this computer architecture study. There are a lot of books available on algorithms for floating point addition, subtraction, multiplication, division. In fact, all different kind of floating point operation available on computing system. If you are interested, you can actually go through the book. These are more like a maths topic than computer science and computer architecture topic. So these are like algorithmic computation for floating point or real numbers. Okay, so these will be out of our scope, but that's very interesting. Like in older computing system, floating point addition, subtraction, and other floating point operations were done through software programs, software libraries. Okay, there is no like a specific digital component in the processor that does the floating point operation. However, in recent computer architecture, these software algorithms has been successfully translated onto hardware, which we call a floating point processor. So they are not part of the main processor, but they are treated as a co-processor. When if your system has such co-processor for doing floating point arithmetic operations, when you write some code to use floating point arithmetics, it uses your main processor uses this co-processor to perform that specific floating point operations. In older computer, older generation, it used to do through the system libraries, which provides algorithm, okay, for computing floating point operations, value, results, and of course this is a software library, so bottom line it will use the hardware system that you have done on the main processor, which consists of mainly your integer arithmetic operation like integer addition, subtraction, multiplication, division, those things. So we'll be in this class we'll be concentrating mostly on the integer addition, subtraction, and other integer operations like multiplication, divisions. Okay, so our topic for this lecture is this, like we'll look at the addition operation and how can we make a digital circuit of this, then subtraction operations. In fact, we'll see subtraction additions are not that different thing. Then we'll see like overflow detection, and we'll try to understand what is an overflow condition, and set less than operation. This is very small thing, but want to mention that how the set less than operation can be done using subtraction operation onto the digital circuit. So let's start with addition operation. So binary addition process is this, right? So we look at how we can add up two single bit, then we'll see how we add up multiple bits, right? The multiple bit represents a value. We all know, I hope you all remember how to do addition, subtraction on paper pencil for decimal representation of any value, right? So the process is very similar to that. Okay, so first we need to know what are the outcome of addition of two bit. Like let's say bit 1 and bit 2, let's say A and B, and we add them. Now if we add them, we have two outcome out of that addition. One is the sum bit, the sum result, and other is the carry. Like for example, in the decimal addition, if you add like for example 9 plus 5, right? So your sum at that stage is 4 and carry is 1 for the next column of the whole number, like for the integer number that you are adding up, right? Let's say 9 and 5 was digit, unit place digit, and you are adding them up. So at that unit place your sum is 4 and carry is 1 for the next 10th place to be add on, right? So that's the paper pencil process. So it's the same thing here. You add up 2 bit and it gives up one sum and one carry. So this truth table shows you, like, if you add up 2 bits, then what is my sum and what is my carry. So this truth table follows that. Now if you think of this decimal addition, paper pencil addition, actually except for the first column, which is like unit place, every other place you actually are doing like 3-digit addition, like even for the two numbers, right? It is the 3-digit addition, because for that place, 10th place or 100th place, you need to add also the carry on from the previous column, right? So you're basically end up doing a 3-digit addition. So same thing would happen here also. In fact, in general, if we want to generalize it, even the first columns, we can think of, we are adding a carry 0, right? We are adding a carry 0, which coming from the previous stage, whatever that stage is. But first column, LSB columns, when we do addition, its carry on is 0. This carry bit is 0 always when we are adding, and that 3-bit addition process is your full addition. Okay, so this truth table is called a half addition because we are not showing the full picture here. We are just involving these 2 bits and it gives up one sum, one carry. But to complete the whole addition process, actually you need to look at the 3-bit addition, because you need to take care of the carry from the previous column or previous stage. So this is half addition. The full addition is we are considering the carry in, that is the carry from the last stage or last column, right? So we'll use that 2 term now. Instead of just the carry, there is carry in and carry out. So each addition stage, each addition column gives you sum, let's say it's called y, the bit y, and carry out from that column, which acts as carry in for the next stage. Okay, so this is the whole truth table for my addition process. So for example, let's say I am couple of examples, like let's say 1 is carry in on the stage, 0 and 1. So it's basically 1 plus 0 is 1 plus 1 is 1, 0. So your sum bit is 0 and carry out from that stage would be 1. Another example, carry in 0, A0, B1. So it will be like 0 plus 0, 0, 0 plus 1, 1, and your carry out from that stage would be 0. And 1 plus 1 plus 1, similar stage, your sum would be 1 and carry out would be 0. So these are these calculation, just I show to whatever I tell, these are the calculation we can do on the paper pencil for one single bit or some one single column of 3 bit, like carry in A and B. Now your addition process, like let's say no overflow, what does it mean is that first of all, like see each stage of addition from each column. So we are adding like an binary value here, 1 1 1 1 0 0 0 0, assuming they're like I'm assuming they're unsigned. Okay, it's nothing, it is not representing a signed component. Let's say it is an unsigned value that we are treating, and we're adding to unsigned value, which is like, oh sorry, this is not the number. The number is 0 0 1 1 1 0 1 0, and another number is 0 1 1 0 1 1 0 0. Okay, the topmost row is showing you the carry bits from the previous column. Now to make the whole process uniform, we are adding an artificial carry in bit for the first column, and we are sticking to 0. This carry in for the first column is always 0. Okay, so just to make it uniform so that each column becomes a 3-bit addition. Now we can say this 3-bit will give me a sum bit of 0 and carry out bit of 0. That 0 goes into next column's addition, and next column become 0 1 0 plus 1 plus 0, which is sum is 1 and carry out 0. This carry out 0 goes as a next column's carry in bit, and it becomes 0 plus 0 plus 1. It also gives 1 as a sum and carry out as a 0 for the next column, and this process goes on for this 8-bit. Now look at the last column. Look at the last column. Last column will also give a sum and a carry out. This last carry out bit, which is from the last, like after the 8-bit, like your result become practically a 9-bit here. So this last bit, the carry out bit, is indicating an overflow. Like what an overflow means is that I am summing up these bits and I am not able to express the sum value with this many bits. I need extra bit for that. Okay, so let's say we are doing 8-bit addition in this case, and we expect our result to be 8-bit. Now if there would be a case, there would be many cases. There 2 8-bit, if you add up, the value cannot be expressed as a 8-bit value. It must have an extra bit. Okay, so of course the reason is that your 8-bit has a range, right? Even unsigned 8-bit has a range from 0 to 255. So if your sum become more than 255, you will not be able to express your sum with 8-bit, right? It needs to have a 9th bit. Now this overflow bit, which is the last carry out from the last bit column, that indicates if you have a successful summation or not. Why? Because if it is 0, then I am sure my sum can be represented within 8-bit in this case, right? Now if it is 1, another example I have given, like this to 8-bit I'm adding up and the same process, but in this case you see the last stage carry out is 1, which means my result of this 2-bit addition 1 0 1 1 1 0 1 0 and 1 1 1 0 1 1 0 0, if we add up, my result, the value it needs to represent, cannot be represented in 8-bit, but it has to be a 9-bit value. Like the result should have been 1 1 0 1 0 0 1 1 0. Okay, but since my result I also want to keep it 8-bit, because like hardware we cannot expand dynamically, right? On paper pencil I can write 9-bit, of course, but if we think of a hardware storage, you are bound with the 8-bit, right? If your system is 32-bit, you are bound with 32-bit, and any value, any operations result has to be represented within 32-bit. If the result occurs to be 33-bit long, or in this example 9-bit long, I am no longer able to represent the result within 8-bit, right? And that's an overflow condition. So the last carry out from the last stage indicates your overflow condition. If it is 0, your sum is good, there is no overflow. If it is 1, that means your sum 8-bit, whatever you are storing into the hardware as a result, that's not the right result because you have an overflow. whatever bit pattern came in, like it's not sufficient, it's not the result basically. That's what it indicates. Now let's look at the half adder circuit. Like we know the half addition, we know the half addition truth table. Then on the, if we are looking at the sum, then look at the truth table. It's practically XOR, isn't it? Right? XOR truth table too. So your sum y is a XOR b, and this is a XOR symbol basically, plus surrounded with a circle. That's an XOR operation symbol. So y is a XOR b, and then if you look at the carry c as an output, that's nothing but a AND between a and b, right? So you have simple one bit half adder circuit here, one XOR gate, another AND gate. That's your half adder.